Ooh, finally, the last section. Oh, I'm sorry. I meant, hi. This is the video 1314 section 4.5. This is the last section of chapter 4, thankfully. And I know that it's applications. An application in Mathyland means word problem. Oh, no. Well, actually, they're really cool. We're going to do word problems for like all of this stuff, but I'm going to use Desmos a lot more, okay? In fact, just because I did it all by hand. I really did. And I wish I could show you. Here, look, here, look. Yeah, you can't see it. So anyways, I did it all by hand. I think Desmos is going to be a lot better for us, okay? So here we go. Applications. They're talking about exponential growth and decay. We had already talked about that earlier. They've given us this new formula, but it's not really a new formula. It's the PERT formula. They're just rewriting it with K's and stuff. But that's fine. We'll see that later. Okay, so they give us an equation, and they say, this is my final answer. How much time did it take? So I'm going to set this thing up, and it looks like my final answer is equal to this original equation solved for t, right? That's basically what they're saying. Now, the method to do this is divide, ln, divide. And we did that. Ooh, don't even have room to fit it all in. Divide, ln, divide. And that's cool. You should do that. You should do that if you want to. But in all honesty, I would say that this is way easier in Desmos. And one of the things about applications is that because it's all decimals, Desmos shines most here. It's not going to like the t's, so put an x instead. Scroll out. Aha, yeah. And then I change that to a minus, and there you go. Again, just reminding you, what I'm doing to change it to a minus is I'm moving this all over to one side so that it's equal to 0, and Desmos understands that better so that it can solve and give you a real answer, okay? So 25.02 years, and it's wrong because you have to add 2003 again. They want AD. Ugh, so annoying. So 25.02 plus 2003, 28. Okay, that's better. I really do. I want to show you this by hand, divide, ln, divide, one more time, and then I probably never use it again. So first, to be able to do this, I'm going to divide by the 722 on both sides. And so then I got this guy is equal to e to the whatever. And then I ln both sides. I'm going to run out of room. You ln both sides, and then you cancel. And then you're going to divide one more time. I mean, I don't even know if the resolution is going to come out to this kind of thing. There you go. I divided that to the other side. There you go. And then you get it, and you get it, and you get it done. Okay. Whatever. I would say that this is a really good method for my other class, the math 1414, the calculus-based stuff. See, and then you just say, oh yeah, answer plus 2003. So like the same thing. It's the same thing. This is a good method for calculus pathway algebra stuff, but that's not this class. And so I don't want to keep going down that road. You guys can use Desmos, so let's do it, you know? All right. Cave paintings says 20% of the original. So what they're meaning is that this final answer is 20 if we're assuming it's an assumption that the original was 100. Okay, it's assumption. Just saying there. So I've got 20 is equal to 100 because these are both percentages. And you can change them to be like 0.2, point whatever. Well, actually, it would have to be like that. But just leave them whole numbers is fine. 00012t. Sometimes that's a 121. It kind of depends on the problem, so watch out for that. I'm going to go right to Desmos. Again, all this stuff is super cool to do by hand in another class, but not this class. This class is not does not like that. Instead of t, use an x. Now, we're talking like cave paintings, so we're talking like pretty far out there. There we go. Again, to make it clickable, often we change that to a minus. There it is. And so 13411 years. There you go. Good enough. Keep going. Half-life. Oh, this is so cool. So we got two cool formulas that Chad made up. That's me. My name's Chad. And so here they are. My K, my rate, is equal to ln of 0.5 divided by the half-life. And then my T time is equal to ln of some kind of a percentage divided by the K rate that we just found. That's a K down there. Okay, so what is half-life? Basically, we have some kind of a substance that's at 100%, and then over time it decays to 50%, and then it'll decay again to 25%, and it'll keep going. But that time that it takes to get from one to the next is a half-life, and then it'll use another half-life, and then another half-life. As we keep going out. So, like, think of uranium, I don't know, 238, something like that. Its half-life is a couple thousand years, I think, something like that. So, over time, it decays, and it'll decay into, like, I don't know, other elements, probably like lead or something. But anyways, there you go. Cool. This also works in other applications, such as, like, drugs that you put into your system. I'm not talking bad ones. I'm talking, like, prescription or, like, pain pills or something like that. There's a half-life. So you take, like, ibuprofen and it helps, but then, like, after 8 hours, it's like, oh, I don't feel the effects anymore because the half-life has drained it down to a point where it's not in your system as much. So half-life is actually a really cool concept. It's very important to us. We use it all the time, even in real life. So all of this is real life. So anyways, even this video, you're watching this video in real life. This is a very simple problem. It says find K, and again, we have the formula is ln of 0.5 divided by half-life. Why do you think it's a 0.5? It's because that's a half-life. Oh. So ln of 0.5 divided by 17.8. Again, like, it's always 0.5. I know some people say, is that always 0.5? Yeah, it's always 0.5. Because it's always half. There you go. So I got negative 0.0389408. I don't know. It says like 6 decimals or something. There you go. Close enough. Cool. That was all they wanted. It was very simple. This is more of an appropriate question. This one I've seen on exams and stuff. It's a really cool problem, very important problem. So here we go. First off, step 1 is find your rate. So that would be the ln of the 0.5. Again, always that. Divided by the half-life. Here's 25. And, oops. Wink. There you go. So I got my rate. They're not looking for the rate, but it's a requirement to go on to the next step. The time to decay down to 91%. So that's that percentage. And notice that I'm writing it in decimal form. So that's my formula is ln percentage divided by the K, the rate that we just found. Okay. So ln of 0.91 divided by the answer we just found. There you go. And what is that, years? Now, pause for a second. See how it says years? And I boxed in the years? On your exam, I remember seeing this, and I remember seeing people getting this wrong. So whatever they have here, you need to click here. It's actually one of the answers. They'll have like days, and they'll have other things, grams, I don't know, whatever weird. If it says years, you put years. If it says days, you put days. Just keep it straight, man. All right, awesome. So half-life of something is 20 seconds. So 20 seconds to get half-life. We're starting with 48 grams, and it says what's going on after 20 seconds. Oh, hold up. Isn't that the half-life? Isn't that the half life? So if I went from 48 and I said half of that, now we're at 24. You did it. And then I did it again. This is actually on my math lab homework. You got to do it again. And then you get 12. Yeah. And then you do it again. It's going to be really tiny. 6. Very good. And then finally, 3. And then you're going to do 3 halves. Yeah, it actually does want that. I can't remember if it wants 1.5 or 3 halves, but one of those answers is still correct. So there you go. Yay! You did it. You just divided by 2. Okay. I think, is this the last? Yeah, it is. This is the last question. Logistic growth model. So this is logistic. It's a little different than logarithmic. Notice that a log, it kind of does like this, but a logistic grows like this, and it kind of like levels off at some point. In the real world, this is a lot more application-based stuff, because in the real world, you have a lot of capping things off. So one of the perfect examples is like population. There's only like say world population. There's only so much dirt for us to like stand on. So there is a max humans that can live here, and I don't know what that is, but there are problems like it on the homework, and they'll talk about it. So yeah, I think they cut like I think it was like 12.58 billion or something like that is what they were estimating. I don't know, but anyways, this is all real world stuff. It's actually really cool, but you know, let's just get the problem done, right? So this one's about the flu, which I don't really like. So nobody likes the flu, but whatever. This one's a very simple problem because we're just going to be plugging things in. It says how many people are sick when it began, and they're wanting to know what the time is. So began means t equals 0. Very good. I'm going to plug a 0 in and get an answer. So I'm going to make this a little bit cooler because we're going to be plugging it in a couple times. There you go. I'm going to write the exact formula up here and then say t equals 0. So whenever I plug in a 0, I get this number, letting Desmos do it all for me. And you know, we're talking about people getting sick and stuff, so you're just going to say, oh, 75% sick, you're sick. So 18. Fourth week, so my t is now equal to 4. Very good, because it says weeks. You put a 4 in, you do it again. I mean, this is easy stuff here, guys. The homework is basically the same way. And then the last one says, what's the limiting size? So how many weeks would this be? I don't know. Let's go for a year. And you notice something interesting is that it's the same as the numerator. So when it says limiting size, they actually just mean the numerator. And in this case, we only got this much. So there you go. All right, we did all of Chapter 4. Isn't that so cool? So next up, we got the Chapter 8, 9, and 11, I think. And then we're almost done. We're like really close to the end of this class. Thank you very much. Have a great day.